be solving other types of equations in your topic 1.4. You know, when we were solving quadratic equations, most of the time what you saw were like x squared polynomials. Sometimes you might have an x to the third or x to the fourth, and you can use other principles with your factoring to solve. So it does say solve each of the following by factoring. And then use the zero product principle. So we can factor it, and then generally from there, even if you have an x squared, we can use the zero product principle from there to finish it out. If you have x to the third, that's your biggest exponent, I know I'm going to have three solutions. Just like with the quadratics, the biggest exponent was generally a 2. You had two solutions. So what by factoring should I be looking for in this first problem? If I'm factoring, I should ask myself, what can I pull out?
Which is x.
Yes. So pull out an x. And remember, if you pull out x, that means I'm left with x squared minus 36. Technically, you could factor that more, but let's just jump right into using the zero product principle, meaning you have x equals 0. This is a factor, even though it's a GCF. And you have x squared minus 36, it's in a parentheses, equals 0. So I know one of my three values. I can go find the other by, I could just use my square root property that we learned, couldn't I? If I move that 36 over there, anytime you have like just an x squared and not an x term, the quicker way to solve is the square root property. So we have x squared equals 36. So if I want to know what x equals and not x squared, reminder of what you did in 1.3, you take the square root of both sides. So x would equal 6, and what else? Negative 6. So remember, to get 36, I could take 6 times 6 is 36, but I could also take negative 6 times negative 6 is 36. So because of this 2, I know I should be getting two things out of that after I square root it. So in WebAssign, whenever you type this in, it's just going to have x equals and then just a box. You're just going to enter those all in. Doesn't matter the order, separated with commas. So it's really easy to forget when we take the square root. It's easy to forget that you get the positive and the negative form of that sometimes. So make a star by it, highlight it or something if you forget. That way you'll be like, oh yeah, I have to have two solutions. Circle it and say, I have to have two solutions. Oops, I about wrote 2 and wrote solution starting with the letter O. So that would be a good indicator and remind you, oh yeah, the other one would be the negative 6. Number 2, I know it's x to the 4th, but can we split 4 in half? Half of 4 is 2. So we could still start by factoring just like it tells you. Solve by factoring, then use the zero product principle. So I could say x squared and x squared. Split the 4's completely just in half. And then what times itself makes 81? 9. And am I using same or opposite sign since it's a negative 81?
Opposite.
Opposite. So that's also a pattern, remember, called difference of two squares. Difference, minus sign in between them. Technically you could factor this one more, but not this one because it has a plus sign. But we aren't going to do that because it's quicker if we just go ahead and set them equal to 0. So we're going to say if I have x squared plus 9 and set it equal to 0, and x squared minus 9 and set it equal to 0, I can go find those 4 solutions. Remember, I know there's 4 solutions because of the x to the 4th. So this is just me, I factored it, and just like I did number 1, and then I set those factors. I didn't think any more about factoring. I just set those factors equal to 0, which is called the zero product principle. Now we just get x squared by itself. So I would subtract 9 from both sides on this one. So I have x squared equals a negative 9. Let's go ahead and do it on the other one. There's a minus 9. Let's go ahead and move the 9 over too. That way we're just kind of doing the same type of step first for each of those. So if x squared equals a positive 9. So you have 2x squareds, meaning from each of these you're going to get 2 different solutions, right? So if I want to know what x equals and not x squared, I take the square root of it. But this is going to be an imaginary number. Is 9 a perfect square?
Yeah.
Yeah, so what you'll have is, you would have to pull an I out, but you'd have a positive 3i and a negative 3i. What about over here? If I take this square root, this one isn't a negative 9, so it's just a positive 3 and a negative 3. So your 4 solutions are right there. 3i, negative 3i, 3, and negative 3. It's fun, right? If I said solve this by factoring, looking at 3, what kind of factoring would you be doing here?
Greatest common factor. Group.
So we could look for
It'd be grouping, right?
It'd be grouping, which includes greatest common factor, so you weren't totally off base, whoever said that. Not all 4 things have the same thing in common, but if I split them into 2 groups, then I'm looking at greatest common factor between the 2 groups, or separate. And you have that equals 0 that's happening over there. So the group that I underlined in black, what do they have in common? X's, x squareds. So let's pull out x squared. Remember, we want to make sure we pull out the smallest, and between the x to the third and the x squared, the smallest was x squared. So x to the third over x squared is x plus x squared, 0 out, so we just have 3. And then the group I underlined in red, what do they have in common? Negative 4, good. We always need to specify if it's going to be negative or positive for sure when we do this part. But since it's negative, we had to have that negative sign there. And if we divide by negative 4,
Should be x plus 3.
yep. So because these are both negative, and I knew I wanted this positive, that's why we did the negative 4, because negative negative makes that positive x.
And this is the same thing. The parentheses are the same.
Yep, so now these are the same parentheses, so we say, okay, we have a like factor, so we can write that down once, and what goes in the other parentheses?
The ones that are in front of the parentheses.
Right, one's in front. So all you did there was, when you were learning solving by factoring back in 1-3, all we did there was factor that. Now we're going to just go ahead and go straight to using the zero product principle, meaning I'm going to stop looking at it at the factoring part. I'm just going to take these 2 parentheses and set them equal to 0 and solve for my x's. The first one is just x plus 3. It's not a squared, so all I have to do is subtract 3 to find its value. So x is just a negative 3. So that's 1. How many solutions are we going to have in this one?
3.
Just 3, right? So we know we'd have 3 solutions. It looks really long. It's a lot smaller looking than 2, and 2 had 4 solutions. But it comes from the exponent. And here we would add 4 over. So you get x squared equals 4. I can't say my values are negative 3 and 4 because this represents x squared. So I have to go find the square root. So x could be 2 or negative 2. I forget to box my stuff out. So hopefully you see in those 3 problems before, it's just kind of like combining some things you learned in 1-3 to be able to solve it. If we look at number 4, rational equations. Remember back in Unit 1 where we talked about solving equations with fractions? Remember that? Seems like a long time ago to me, personally. I'm sure it seems like it never happened to you. Right? You just kind of like, you did it, you pigeonhole it, and you move on, don't you? It's okay, I do too. We kind of learned that you were going to clear the fractions in the very beginning. And I will tell you, technically you could do that in these, but I'm going to teach you an easier way on these types of problems. Rational equations is just a description of an equation that has fractions with polynomials in it. Maybe got binomials in the bottom, or all kinds of stuff that happens. They can get really complex. About as complex as we're going to see are like the 2 examples I'm giving you today. But what I want you to identify to make it a little bit easier is if you have 2 fractions that have the same denominator, and we do, right? And so what would be really nice is if they were on the same side so that we could like add or subtract the tops just to make one fraction, just to kind of simplify it. So if that was a negative 5 over x minus 5, I could add 5 over x minus 5, and that would like zero that out. It looks a little more complex because you have the denominator, but let's just pretend that since we know they have the same denominator that we're just saying negative 5 and 5 zero out, right? Because that's what you're doing when it comes to fractions. So I'm going to write this over here. I'm not a real big fan of working fractions vertically. I'm just going to show you over here what it would look like. This would be like saying I have x over x minus 5, and like I'm adding 5 over x minus 5. So since they have the same denominator, we keep it the same, and we just add the tops. But are the tops like terms? No, so we're just going to make an expression, x plus 5. So when we do this, I think visually it's easier to see it like this. I'm just going to put a star there because we just have x plus 5 over x minus 5. And now over here we just have 1. Now if on the other side that wasn't a 1, do you guys remember if you have a fraction equaling just one other fraction or one other something you could butterfly? Kind of remember that from Unit 1 a little bit? We could do that here, but since this is a 1, you could just stop and say, is x plus 5 divided by x minus 5, is that 1?
Yeah.
Be careful. It's very similar. They would have to have the same exact signs.
It'd be negative 1.
So it wouldn't even be negative 1. But we're thinking on the right track, sort of. It's just, this cannot divide into that, right? We couldn't like cancel it out and say, yeah, that's 1. So actually, it doesn't happen a lot, but there would be no solution on this one. I kind of hate that we lead off with a no solution one with irrational expressions, but here we are doing it. If this was like an x plus 5 over x minus 5 equals a different number than 1, like 2, or maybe 2x, or maybe x plus 7, I don't know, we could then like butterfly it and go solve for x's, which we'll do on the next one, but sometimes you are going to get no solutions, but not that often. But this one is only because we're equaling 1, so this is not possible, basically. Now, if you had x plus 5 over itself, that would be possible. That would be just 1. But it's not, so x would just be 1. But that's the difference, and it's just because of the signs. But let's do one that we can actually do something with. So when you're looking at these, what I want you to try to train yourself to do is now just say, okay, I'm going to look at the denominators. There's a lot of stuff happening in the denominators. But let's see, do we have anything that's the same? And I have x minus 3's that are the same. So what would make this a lot easier is if those x minus 3's were on the same side. And we know how to do that now. We know how to move terms. So let's do that. Let's say I want to take this. It's kind of hard because I can't really write over the black, but and I want to move that over here. So since that's a positive fraction, let's just think positive 8. I would subtract 8, but we keep that x minus 3 underneath. And I'm going to write this one horizontally just because it is so much easier to process fractions when they're side by side. So by taking 8 minus 8, we got rid of that. Since there's a minus sign in front of this one, we're going to give it to the 3. I'm going to say I have negative 3 over x minus 4 equals, since we have 7 minus 8 up here, are those like terms?
Yep.
This time they are. Last time it was like a letter and a number. But we can actually take 7 minus 8, kind of smudged my red pen, but that's a negative 1. And then we keep the x minus 3. Now you could just butterfly these. Do you remember butterfly a little bit, maybe? You just take the one top and multiply it times its opposite's bottom. So negative 3 over x minus 3, like diagonals. Just be sure you put an equal sign between the opposite one that you're doing.
Would it be okay to be like negative 3x plus 9, or do you not want to do that?
You can. I just write the steps because sometimes when you go back and look at your notes, you don't remember how you got that.
Oh, okay.
So I just set it up so that you can see the multiplication of the or the setup before the multiplication. If I were doing it, I would probably do that too. But notes especially, even if you could do that, I would write it down. Just that way when you go back and look at your notes, you know what happened from here to here. So we're distributing negative 3x. Negative times a negative is a positive 9. Equals negative 1 times x. Negative times a negative makes that a positive 4. And now we're just down to our normal solving equation skills that we already know. We have variables on both sides and we have constants on both. Technically, you can start 4 different places. Since I'm teaching, I get to start where I want to start. I generally, when I can, move my variable to the left. It's just what I do. I try to be consistent in case somebody's very patterny and doesn't like change. Maybe that's also me, I don't know. So I would add 1x to both sides because negative 1 plus 1 would 0 that out. So we have negative 3 plus 1 is a negative 2x. For space, I'm probably going to show that I'm moving my constant here too. Since that's a positive 9, I would subtract 9, and that's going to move the constant over there. So 4 minus 9 is a negative 5. What's between those? What do I have to bring down?
Equal sign.
Yeah, just don't forget to bring down your equal sign if you do it like that and you don't rewrite it for the next step. And then we finish solving by dividing by negative 2. So x equals a positive 5 over 2. Because remember, those have negative signs, so it means it's really a positive fraction. So, I think when you're solving rational equations, the biggest thing I hope that you'll get from it, like I said, I'm just going to repeat it again, is if you could have fractions on the same side that have the same denominator, it's just going to make it a lot easier to tackle than having to clear out the denominators. Clearing out the denominators in this one would look like multiplying this times x minus 4 and x minus 3. So that the x minus 3's cancel, then you'd have to distribute. Same here, and then same here. And that's a lot of writing and seems like a lot of steps. Kind of overwhelming almost. So if we can kind of switch our thinking a little bit to clearing the denominators is good. But in one like this, if you have like denominators, get them to the same side and only those guys that have the same denominators on that side. And then see if you can add or subtract what's in the top or make a polynomial up there. And then you can butterfly, and it just makes it a lot easier, a lot less overwhelming in steps. We have two more different types of equations that you'll see in algebra. One is radical equations, and the other would be rational equations that have rational exponents. But let's do our radical equations first. So on these radical equations, notice it says solve and check. Sometimes I forget to check too, but you have to check these. It's required because sometimes you'll solve and a solution doesn't really work. It's called an extraneous solution, which means it wasn't a real answer. With radicals, that happens because when you take square root of a number or square a number and signs, things aren't always exactly as they seem. Okay, it's a little, it's not always going to work, basically. But one thing you need to be sure of is that your radical is by itself. It makes it the easiest if you can. This one is by itself already. I'm just going to highlight it. So what's the opposite of square rooting something?
To the second power.
Yeah, take it to the second power. So we want to undo this by squaring it. What that does is it cancels out that radical symbol, and it's like that radical symbol just goes away from being above the 2x minus 3. So you just have 2x minus 3, and we say equals 7 squared is 49. So then we'll go just finish solving for x. So this is easy, it's just an x, it's not a squared. We don't have to worry about quadratics. So we just do our normal solving stuff. So we have 2x equals 52. We divide by 2 and we get 26. So before you would go into WebAssign and type in my answer is 26, you should check it. A lot of times they are going to work in WebAssign. I can't really remember if any of them don't or not off the top of my head right now. I know I'm pretty nerdy and I like math, but I don't memorize your homeworks. Surprise. I know that seems like I would, but I don't. So we would just go plug it in. 2 times x, and we're saying x is 26 minus 3 equals 7. So we just want to see if I simplify this left side, does it equal 7? So you can just, in your calculator, type that in the square root of 2 times 26 minus 3, and that is the number 7. So 7 does equal 7, so it would be a real solution, but it only took you half a second to do that. It didn't take all that long. It took longer for me to explain it than to do it. 7, though, is not really in a good starting point when we're working with equations with radicals. It's okay that the square root has a number right in front of it. You can actually keep that in front of it, but we don't want to have the x plus that there. We want to move that x, so what we would do is, since it's a positive x, we would subtract x. Because to undo that radical, we're going to have to square each side, and you would have to go through and FOIL that, and that would be very busy, and you would hate it. So 2 times the square root of x minus 1 equals, and we can keep this as 9 minus x. You don't have to put that in descending order. This order is fine for what we're doing right now. I will tell you, if this was just like the number 10 over here, wasn't a binomial, it would be easier if you just divided by 2, because you could. But if I divide by 2 right now, that side's going to look way complex, and when I square that, that's going to be more than I want to do. So we're going to keep that 2 there and just square both sides. And when you do that, the easiest way for me to explain this side that you're squaring is your 2 is getting squared separately from your radical. So if you kind of pull it apart like that, that helps you see what's happening with those. There's a longer explanation, but to make it simple, let's just pull it apart and know that, kind of like when you had 2a and you squared it. I know a is just a letter, it's not a radical, but your squared went to both things, right? 2 times 2 is 4. So we're doing the same thing when there's a number in front of the radical. So that's 4, and then this cancels that, so there's a binomial under there, so we're going to put it in a parentheses, x minus 1. Because this is a binomial squared here, we're going to need to expand it, or you might think FOIL this, so we need to write it twice, 9 minus x times 9 minus x. So we're just going to go through our FOIL steps. 9 times 9 is 81. 9 times negative x is a negative, I wrote 91, sorry. I said 81, I think. 9 times negative x is negative 9x. Negative x times 9 is a negative 9x. And a negative times a negative makes that a positive x squared. So when we solve this, because of the x squared, we're going to have to solve a quadratic. So you're going to be solving quadratics like from here on out if you're ever solving an equation for some reason that has an x squared in it. Factoring is the easiest when you can. You can't always factor, but first thing I would need to do if I was going to do the factoring, or even if I was going to use the quadratic formula, is everything has to be on the same side anyways, right? So we need to get rid of the parentheses over here. So we have 4x minus 4. And I would probably go ahead and put this in descending order, knowing that I might want to factor it. So since that's a positive x squared, I'm going to write x squared. I have some like terms right here. Negative 9 and negative 9 make a negative 18x. And that's a positive 81, so I would just write plus 81. So I kind of did two things at once in that step. I combined like terms and put it in descending order. Did you guys get that? Okay, so I'm trying to get everything on the same side, so I'm going to subtract 4x and add 4 with its like terms on the other side, so that these will zero out, so one side equals 0. And then I have x squared minus 22x plus 85. And then from here, this is when you get to decide how you want to solve a quadratic equation. Factoring, if it factors, should be the fastest and easiest way. This one does factor. If you take 85 and divide it by 5, that's 17. So if you don't know those, just write in your head that you can use your calculator to go through factors quickly. And I know 5 times 17 is 85. And if they're both negative, wouldn't they add up to make negative 22? Yeah, so those are the pairs I'm going to use. I didn't go through all the factors just for time purposes, but like if you wanted to check, you can go through all the factors of 85 to find your pair. A lot of times if it's a number ending in 5, I go, especially if it's a big number, I start there. So we plug in minus 5 and minus 17. And then what's our next step when we're solving by factoring? Set them equal to 0 separately. And that gives you your two values for x once you solve. So here I would have to add 5. Here I'm having to add 17. So it's kind of a lot of steps. I know it tests your math endurance when you're doing some of these problems. Some things get really long. Later when we do other things, some things just take a lot of steps. I wouldn't though, after doing all that, I just spent like probably 5 minutes doing that with you, I don't know. But I can't just say my answer is 5 and 17 because I already know, because I've done this a lot of times in my life, I already know one of these doesn't work. But you wouldn't know that, so you have to check it to see. So if you were to plug in 5, 17, WebAssign's going to say, no, that's not true, because only one of these solutions really works. So you do that by checking it. So the original problem was x plus 2 times the square root of x minus 1 equals 9. And so when you check, you're just plugging those values in for x to see if it really does equal 9 or not. So I'm going to just write it down. A lot of times you may just type this in your calculator, and that's okay too. But since we're taking notes, I'm going to write it down so you know that we checked it, and we know why one works and the other doesn't. So we're going to type in 5 plus 2 times the square root of 5 minus 1, which is 4. And so we know that x equals 5 does work. So now I'm going to check the other one. I'm going to plug 17 in for it. So 17 plus 2 times 17 minus 1 equals 9. So we just type in 17 plus 2 times the square root of 17 minus 1, and that's 25. So does 25 equal 9? No. So this one would be considered extraneous, is the technical term. You don't have to know that verbiage technically, but if you were given this problem on WebAssign, you would only enter 5 in for your answer.
And so only one, if you get like 2 answers like that, only one of them's gonna work.
Not always.
So both of them could work.
Mm-hmm.
Okay.
Yeah. Those of you in Zoom, if you didn't hear, the question was, well, if you have a quadratic and you get 2 equations, will one always not work? And that's not true. Sometimes they both actually do work, but sometimes one doesn't work. Sometimes when you're solving one of these that only has one possible answer, sometimes it doesn't really work. And then you would just say there's no solution if that happens. If you plug it back in and it didn't really work, and you only had one choice, you would say no solution. Okay, last thing. On 1.4, and then you can take a little bit of a mental break. So solving an equation that has a rational exponent. So a rational exponent is something that's raised to a fraction power. That's what a rational exponent is. This one's already in a really good starting spot. You want your variable to the power to be isolated, so this one's already like that. But if you think about what this means I don't even have a full x. I have 2/3 of an x, like 2/3 of a pizza. But you want a full x, a x to the understood 1 power. And if you remember about fractions, if you multiply times its reciprocal, that makes that a 1. So if you do it on the left-hand side of the equal sign, which is what we just did, you have to do it on the right-hand side. 16 has an understood 1 exponent, but 1 times 3 over 2 is just going to be 3 over 2, right? So I just like to write 3 over 2 over there as its exponent. So in your calculator, you can just type this in. You don't have to do this manually. You can just say 16 to the, and then you use your fraction key up there in your exponent, and you type in 3 over 2, which is 64. I'm going to remind you in a minute when we get done with number 9 that you did learn how to simplify rational exponents back in your pre-algebra days, or algebra 1 days probably, but I'm going to go ahead and move on to number 9, and then I'll just review that concept with you separately. Because what happens with this is it actually turns into a radical. Do any of you remember that? We'll go over that later, in a minute. So in number 9, we do not have the letter raised to the 3/4 power. We don't have it isolated, so the first thing we would want to do is isolate it. So I'm going to add 44. I'm probably going to write it to the right just because I don't have a lot of space here. I probably should pull this up in the future. So 2x to the 3/4 power equals 54. And then to get that x by itself, I'm still just dividing by 2, so kind of ignore the fact that it has a weird exponent. So x to the 3/4 power equals 27. And this time I kind of write it vertically. I think it's just easier to visualize. If you have x to the 3/4 power and I want x to the first, you just multiply that 3/4 times its reciprocal of 4/3. So if you do that over here to this exponent, you have to do that over here. Again, 27, I don't usually write it, but is understood to be over 1. We don't write those understood ones because that would be really busy. And when we multiply times 4/3, it's just that. So to kind of eliminate busy writing, I don't do that. So in our calculator, you have x equals, and you're just typing this into your calculator right there, 27, and raise that 2, and you hit your fraction key and type in 4/3, and it's going to be 81. And anything I give you should not end up being in the radical form anyways. It should end up being a whole number. So if you type that in and you get something weird, it's probably because you didn't flip the fraction right. Sometimes we know to flip the fraction, but we don't. I don't know. Our eyes get all jumbled or something, and maybe we still just type it in as 3/4. So if you get a decimal, you probably have done something wrong with either your calculator or when you flipped, you really didn't flip it. It should become a whole number when you do it. So just a little concept review, because you need to know it when we go on to logarithms later, which you probably at the end of the semester will not be like, yeah, on September 27th, you went over this, I remember that. But I'm going to anyways, just because I think it's good. If we take 16, what was it? What did we raise it to the, I should know. And we raise it to the 3/2 power, or 27, and raise it to the 4/3 power. These actually convert into radicals. That's where radicals come from, our rational exponents. So this number is your index or your root, whichever word you like to use. So like it's like we're taking the square root of 16. I didn't have to put the 2 there, but I did just to emphasize it. And then you would raise it to the 3rd power. So the square root of 16 is 4, and when we cubed it, we got 64. So that's basically what your calculator did for you. And we do have to know that later. We do have to kind of understand how to convert those exponents to radicals, or radicals to exponents, like that. And this one would be like saying the cube root of 27 to the 4th power. And you may not have cube roots memorized, or maybe you do, but 3 times 3 times 3 is 27, so that'd be like 3 to the 4th power, and 3 to the 4th is 81. But that's just a concept review of something that you did learn a long time ago, you may have forgotten.